Tonight, starlight becomes a quiet messenger. It slips through distant atmospheres and returns with subtle changes. Soft dips and faint slopes carry clues of molecules, clouds, and drifting haze. No engines, no voices, only light moving through layers at the edge of a world. This is Space Dreams documentary. If this calm journey helps the mind slow down, please like the video and subscribe for more long-form cosmic sleep documentaries. Now, the story begins gently, one wavelength at a time. At the edge of a distant transit, light becomes thinner in a way that can be listened to. The atmosphere reveals itself by removing a few colours from starlight as it skims the planet's rim. In that region, a dark disk crosses a bright face, and a faint ring of air quietly edits the spectrum. The scene holds on a clean silhouette first. A shallow notch appears in the brightness. It is small enough to feel like nothing. Yet that notch carries a map of gas and height. A signal would seem to come from a simple shadow. The important detail is that the shadow has a soft boundary. The boundary is the atmosphere. It is not a hard edge. It is a gradient that thickens toward deeper layers. As the planet moves, the line where night meets day traces a slow arc. Along that arc, a sliver of starlight passes through air before escaping. Some wavelengths pass almost unchanged. Other wavelengths are absorbed more readily. The result is a transit depth that depends on colour. The planet looks slightly larger in colours that are absorbed. It looks slightly smaller in colours that slip through. This is the core idea of transmission spectroscopy. It is a way to read an atmosphere from the size of a shadow. A gentle payoff follows from geometry alone. If absorption is stronger at a wavelength, the effective rim sits higher. The light is stopped earlier. The atmosphere becomes a measuring stick made of starlight. The visual slows into a narrow luminous crescent around the planet's limb. That crescent is not bright in itself. It is borrowed light that has been filtered. In that borrowed rim, the difference between clear and absorbing air can be no thicker than a thin skin. The scale can still matter. A typical atmospheric signal can be about 1 part in 10,000 of the star's light. That is like noticing a single dark hair floating on a pale bowl of milk. It is not dramatic. It is precise. A second payoff arrives in the shape of the spectrum. The missing light is not missing at random. Gases absorb at specific wavelengths because molecules have allowed vibrations and rotations. A new term can enter once and then fade. A spectrum is light spread into its colours. The pattern of small dips across those colours becomes a fingerprint. Not a perfect fingerprint, not a complete biography, still a recognisable signature. In that region, the spectrum looks like a calm ribbon with a few shallow bites taken out. Each bite is a clue to what sits in the air. The visual anchor shifts to a long band of colour that darkens in thin stripes. Those stripes are not equally spaced. They have families. Some are narrow, some are broad. A gas with a strong band can leave a wide valley. Another gas can leave a fine comb of lines. The mind wants to label each dip and feel finished. The atmosphere refuses that simplicity. Temperature and pressure smear the marks. Higher layers are thinner. Collisions are rare. Features can be sharper there. Lower layers are denser. Collisions broaden features into softer troughs. The limb becomes a stack of conditions. A single wavelength can sample several heights at once. A third payoff comes from that stacking. The transit spectrum is not a straight list of molecules. It is a blend of composition and structure. A deep dip can mean an abundant absorber. It can also mean a tall atmosphere. A shallow dip can mean a scarce absorber. It can also mean clouds cutting off the view. The physical detail is always present at the limb. There is a pressure gradient. There is a curved path through the air. There is a long slant column that increases the amount of gas encountered. The same atmosphere that would seem thin from above can look thick from the side. The everyday analogy can hold the idea without strain. A thin scarf held in front of a lamp can dim certain hues more than others if its threads are dyed. From straight on, the scarf seems modest. From a grazing angle, the threads overlap and the tint deepens. In transmission, the grazing angle is the rule. Light behaves as a traveller that takes the long way through a border. The border is where the atmosphere speaks most clearly. The visual slows again. The planet's rim is traced as a pale outline against the stellar disk. The outline is uneven in meaning. In some colours it rises higher like a thicker haze line. In other colours it sits lower like clearer air. The story stays calm because the changes are small. The importance grows because the consequences are large. A shift of only a few tens of kilometres in effective height can decide whether a molecule is present. A few tens of kilometres is like the height of a tall mountain range. It is tiny beside a planet. It is huge beside a spectral notch. The scale shift is gentle. It moves from the trembling of a bond to the size of a world. It moves from a narrow band of colour to the history of an atmosphere. Once a gas is inferred, it hints at chemistry. Once a scale height is inferred, it hints at temperature and mean molecular weight. The atmosphere starts to become a climate, not just a list. The calm promise begins to form. If the rim can be read, then the layers can be untangled. If the layers can be untangled, then clouds and hazes can be recognised as masks rather than mysteries. Another visual anchor arrives in a slow glide through the limb itself. Imagine a cross-section at the terminator. The lowest layers are thick and dark in absorption. Higher layers are thin and bright in transmission. A subtle boundary appears where opacity rises fast. That boundary can be a cloud deck. It can be a haze layer. It can be a region where a molecule becomes abundant. In that region, the spectrum changes slope. A gentle payoff follows. A flat spectrum across many wavelengths often means that something is hiding the deeper air. A sloped spectrum can mean scattering from tiny particles. The signal is not only a fingerprint, it is also a silhouette of structure. Now the limits arrive softly because the rim is also where deception thrives. The spectrum is extracted from tiny differences between two large numbers. The star is bright. The transit is a small subtraction. Any imperfection in the baseline can mimic absorption. Spots and bright patches on the star can change the effective colour of the light that is blocked. In that case, the planet's shadow crosses a surface that is not uniform. The measured spectrum can inherit the star's texture. A second limit sits in the mathematics of inference. Different combinations of temperature composition and clouds can produce very similar spectra. The result is a family of solutions rather than a single answer. The limit is not a failure. It is a property of indirect measurement. The rim does not give a photograph. It gives constraints. The calm way forward is to treat each dip as a question that can be tested by consistency. Does the feature repeat across time? Does it fit with neighbouring wavelengths? Does it survive when the assumed stellar surface changes? A visual anchor holds the caution. Two nearly identical spectra lie on top of each other like thin sheets. One has real molecular structure. One has a false dip caused by an uneven stellar limb. They differ only by subtle curvature. That is the trap. The atmosphere is read through the star. The star is part of the instrument. The mind wants certainty. The data offers probability. Another payoff arrives in that restraint. When the limits are acknowledged, the remaining signal becomes more trustworthy. The spectrum becomes a quiet conversation between physics and light. It does not shout. It accumulates. Over multiple transits, stable features deepen while random noise fades. That accumulation is not shown as a machine or a screen. It is shown as repeated shadows crossing the same bright disk. Each crossing leaves a faint imprint in memory. The imprint sharpens with repetition. The final visual slows into a nearly motionless moment. The planet nears the centre of the stellar face. The limb ring is present all around. In some colours the ring seems slightly thicker. In other colours it seems slightly thinner. The whole method rests on that difference. From that small difference, composition and structure can be approached without touching the world. The next step is to understand how layers and pressure decide which heights are even visible. The rim remains in view as the scene eases towards stacked atmospheres and the quiet logic of depth. A planet's shadow stays simple, yet the air around it is layered. The transmission signal mainly comes from a narrow range of heights. where the limb becomes neither fully clear nor fully opaque. In that region, the atmosphere is not a single shell. It is a stack of pressures that fade upward. The fading is smooth. It has no sharp edge. The limb path cuts through that fade at a shallow angle. Light behaves as a skimmer that spends a long time near the horizon. A small change in density can matter more than expected. The reason is length. A vertical column is short. A slant column is long. The same gas can look thin from above and thick from the side. The first quiet payoff is that height becomes a dial. If the atmosphere is tall, more layers participate in the filtering. If the atmosphere is compact, the useful limb is squeezed into a thinner band. The visual anchor settles into a cross-section at the terminator. Low layers look dark and crowded. Higher layers look pale and sparse. Between them sits a smooth gradient like fog thinning into clear night. The gradient has a name that can enter once and then soften away. Scale height is the distance where pressure drops to about 1/3. One scale height might be about 30 kilometers, like stacking 3 deepest ocean trenches from rim to rim. That distance is small beside a planet. It is large beside a spectral dip. Another payoff follows from the same idea. A larger scale height makes absorption features taller in the spectrum. The planet appears slightly larger in absorbing colours because the effective rim rises. A smaller scale height makes the same absorber look quieter because the rim does not lift as much. The spectrum is not only about what the gas is, it is also about how far the gas spreads upward. The scene slows on the limb again. The curved path of light is traced as a thin arc that grazes the planet. Along that arc, the air density changes with height. The change is exponential in feel. The lower layers add a lot at first. Then each step upward adds less. Yet the limb geometry compensates by giving upper layers a long path length. This is why thin air can still imprint a signature. It is also why deep layers can be hidden. Once a layer becomes opaque at a wavelength deeper, layers stop contributing. The spectrum becomes a record of where opacity turns on. The physical detail is a boundary that is not a surface. It is an optical boundary. It sits at the altitude where the path finally blocks enough light to matter. A quiet payoff appears here as well. That optical boundary shifts with wavelength. It shifts upward where absorption is strong. It shifts downward where the air is transparent. This shifting turns a spectrum into a vertical probe, but only in a blurred way. The blur is gentle and unavoidable. The limb mixes many altitudes in one measurement. A narrow line of sight still samples a range of heights, because density and path length trade places along the arc. The everyday analogy holds the blur without strain. Imagine a stack of translucent paper sheets tinted with faint dye. Looking straight down the stack seems modest. Looking along the edge, many sheets overlap and the tint deepens. The edge view does not reveal a single sheet. It reveals the combined thickness that finally looks coloured. In transmission, the limb view is that edge view. It favours the heights where the overlap becomes noticeable. Another visual anchor arrives as a slow sweep upward through layers. Near the bottom, collisions between molecules are common. The air is crowded. Features are broadened and softened. Higher up, collisions are rare. The same absorber can carve sharper structure. The spectrum can carry hints of both regimes, but it rarely separates them cleanly. A quiet payoff emerges from this contrast. If a feature is unusually broad, it often points toward denser layers or higher pressure. If a feature stays narrow, it often points toward thinner layers or lower pressure. The atmosphere reveals not just presence, but environment. The signal gains texture. The scene stays calm by returning to the rim. The rim is thin and bright against the stellar face. It is also where clouds and hazes can set a ceiling. A cloud deck is a physical layer of particles that becomes opaque. In transmission, it acts like a lid. Below the lid, deeper gases may exist. Their signatures may never reach the escaping light. Above the lid, only the upper atmosphere speaks. The spectrum can flatten when the lid is high and bright. The spectrum can tilt when small particles scatter short wavelengths more strongly. The payoff is practical. A featureless spectrum does not mean a barren atmosphere. It can mean a masked one. A steep slope does not require a new molecule. It can arise from scattering by a haze. The visual anchor becomes a pale veil wrapped around the terminator. The veil is not uniform. It thickens where particles cluster. It thins where the air is clearer. The boundary of the veil is soft. It fades into the upper layers. Now the limit of intuition arrives, stated softly and precisely. Vertical resolution is limited because the limb integrates many heights into one curve. A single dip in the spectrum cannot be assigned to a single altitude. It is a weighted blend that peaks near the optical boundary. Another limit follows from inference itself. Temperature means molecular weight and scale height can mimic each other. A warmer atmosphere can look taller. A lighter atmosphere can also look taller. A cooler, heavier atmosphere can look compact. The same spectral amplitude can match more than one physical story. The limit is not a mystery. It is a degeneracy in indirect measurement. The quiet way forward is to use multiple wavelengths that probe different opacities. Strong bands sample higher layers. Weak bands sample deeper layers until a cloud lid stops them. The combination can narrow the family of possibilities. The scale shift widens without hurry. A vibration inside a molecule lasts a fraction of a second. The imprint of many such vibrations can persist in a spectrum across countless orbits. The layering that shapes a transit can be altered by winds and mixing. Over long spans, chemistry and lost to space can rebuild the whole profile. Yet the measurement remains a momentary slice. It is the atmosphere caught in silhouette at a single alignment. The final visual slows into a quiet stack of horizons. Each wavelength finds its own horizon height in the limb. Some horizons sit high in thin air, others sit low until blocked. The next step is to treat wavelength itself as a ruler. The spectrum becomes a set of measuring marks across colour, each mark pointing to a different depth. Colour seems continuous until a spectrum turns it into distance. Wavelength acts like a ruler because different colours reach different depths in the limb. At this distance, the planet's edge is not one boundary. It is many boundaries stacked by opacity. One colour sees deeper, another colour stops higher. The atmosphere becomes a set of nested rims that shift with wavelength. The first payoff is simple. A deeper reaching colour measures denser layers. A higher stopping colour measures thinner layers. The visual anchor settles on the transit silhouette again. Around the dark disk, several faint rings appear in the mind's eye. Each ring belongs to a different part of the spectrum. The rings do not glow. They are inferred borders where the slant path finally blocks enough light. Some rings lie close to the solid body. Some sit higher in a softer halo. The rings form a quiet topography. The planet's apparent size changes by tiny amounts across colour. Those tiny amounts build the transmission spectrum. A new term can enter once and then soften away. Opacity is how strongly matter blocks light at a wavelength. One sentence definition holds. Opacity decides where the limb becomes effectively opaque. Two example sentences follow. In clear air, opacity is low and the boundary sinks. In absorbing air, opacity is high and the boundary rises. One sentence completes the loop. This is why wavelength becomes a depth gauge without touching the atmosphere. The physical detail is a gradient that never stops. Density falls upward. Pressure thins. The slant path lengthens near the horizon. Light behaves as a traveller that stays near the rim longer than expected. That long glide makes upper layers matter. The second payoff arrives from the way strength varies. A strong absorber does not merely add a deeper notch. It moves the effective boundary upward by multiple scale heights. A weak absorber moves it less. A typical strong band can lift the boundary by about 5 scale heights, like 5 tide lines stacked on a dark sea cliff. The number is modest. The consequence is not. Each lifted line changes the planet's apparent radius by a thin shell. The shell is small beside the world. The shell is large beside the signal. The visual anchor deepens. The nested rings look like contour lines around a hill. Each line traces a different altitude where the atmosphere turns opaque for that colour. The lines are smooth at first, then they become slightly uneven as the limb samples different heights. The eye rests on the terminator. A shallow arc divides day from night. Along that arc, the rings lean outward where opacity rises. They lean inward where light slips through. The spectrum is built from those leanings. The payoff is immediate. Measuring the shift across wavelength measures how opacity changes. Measuring how opacity changes begins to separate gases from structure. Now the ruler gains markings. Some wavelengths belong to the continuum. They are places where opacity is low. They act like clear windows that look deeper until a cloud deck stops them. Other wavelengths sit inside absorption bands. They are places where opacity is high. They look higher into thinner air. This is a gentle checkpoint. The same atmosphere yields two different views at once. The continuum view is the deeper baseline. The band view is the higher crest. The difference between crest and baseline is the amplitude of a feature. That amplitude carries the story of scale height and clouds. The visual anchor shifts to a calm ribbon of colour. The ribbon dips into shallow valleys. Between valleys, the ribbon rises toward the continuum. Each valley has shoulders. Each shoulder slopes gently. The slopes are not decoration. They come from physics. Temperature broadens features. Pressure broadens them deeper down. The wings of a band can probe lower than the core. The core can probe higher than the wings. A single absorber becomes a ladder of depths but with blurred rungs. Another payoff follows from that blur. When only the core is seen, the atmosphere above clouds is being sampled. When the wings are also seen deeper, layers are being reached. The spectral shape becomes a kind of vertical hint. The hint is subtle. It requires patience. It also requires that the ruler is not smudged. The limit of observation arrives softly here. Spectral resolution limits how finely the ruler is marked. If colours are blended into wide bins, narrow absorption lines merge into a shallow trough. The true depth can be underestimated. The true shape can be lost. Another limit sits in the baseline. Small errors in the continuum slope can imitate scattering or hide it. The ruler can be bent by systematic trends. The method still works. It just demands caution. The measurement is a difference between two nearly equal brightness levels. Any drift in the baseline can look like a feature. In that region, the star's limb darkening also matters. The stellar edge is dimmer than the centre. The planet does not block a uniform surface. The colour-dependent brightness profile of the star can tilt the inferred spectrum if not handled carefully. The payoff of admitting this is calm confidence. A feature that survives different assumptions is more likely to belong to the planet. A feature that changes with baseline choices is treated as uncertain. The ruler becomes honest when its own bending is known. The analogy returns with natural steadiness. Tide lines on rock record repeated water levels. A single line can be misleading if the sea is rough. A set of consistent lines spaced in a coherent way reveals the true rise and fall. The spectrum behaves like that set. Individual dips can be ambiguous. Families of dips that match a single opacity law are persuasive. The visual anchor widens again. The nested rings around the planet are now imagined across many wavelengths. Some rings cluster closely, some spread apart. Where rings spread apart, opacity changes rapidly with wavelength. Where rings cluster, opacity is smooth. This spreading and clustering is the beginning of a fingerprint. The scale shift broadens without strain. In the microscopic world, molecules rotate and vibrate. Their allowed motions decide where opacity spikes. In the macroscopic world, those spikes decide where the limb boundary sits. The sitting boundary decides how large the planet appears. The appearance is measured over a transit that lasts only a few hours. The implications can reach across eons of atmospheric evolution. A thin difference in opacity can hint at a lifetime of chemistry. The ruler also has a hidden ruler behind it. The pressure scale sets the spacing of layers. The temperature sets the thickness of the atmosphere. Both modulate how strongly the rings move. The spectrum therefore carries a mixture of effects. The limit of intuition is gentle here. The mind wants each wavelength to correspond to a single height. The limb refuses that. The slant path samples a range. The effective boundary is a weighted blend. It shifts smoothly, not in steps. This is why retrieval is cautious later. The ruler is not a drill. It is a soft probe. Another payoff follows from accepting softness. Because the probe is soft, broad trends across wavelength become valuable. A haze can impose a smooth slope. A cloud deck can impose a flat ceiling. Molecular bands can impose structured valleys. Each leaves a different kind of ring pattern around the limb. The final visual anchor returns to the ribbon of colour. The ribbon is now seen as a landscape. Broad plains mark clearer windows. Gentle hills mark scattering. Distinct ravines mark molecular absorption. The next step is to learn how molecules carve ravines with repeating shapes. The spectrum's ruler becomes a library of fingerprints, and the nested rings begin to name the gases that shape them. A spectrum looks like a quiet shoreline until patterns begin to repeat. Molecules leave recognizable gaps because each kind of bond prefers specific colors. In that region, the limb acts like a thin archive of air. Light passes through it and returns carrying missing pieces. The missing pieces are not random. They gather into families. A single molecule can stamp about a dozen prominent bands like a simple flower, showing a dozen petals around a calm center. The first payoff is immediate. Repetition is the sign that the absorber has internal structure rather than chance noise. The visual anchor settles on a long ribbon of colour laid flat like a calm horizon. Along the ribbon, small valleys appear. Some valleys arrive in groups. The spacing is not uniform, the depths are not equal. Still, the group holds together as a motif. Light behaves as a sorter that reveals these motifs by subtraction. A new term can enter once and then soften away. An absorption band is a range of wavelengths where a molecule blocks light. One sentence definition holds. 2 example sentences follow. A band can be broad when many nearby lines overlap. A band can be narrow when only a few lines contribute. One sentence completes the loop. The band shape matters because it sets how the limb boundary shifts with wavelength. The physical detail remains the same. The rim is curved. The path length is long near the horizon. The density falls upward in a smooth gradient. Within that gradient, a molecule is not a point. It is a set of masses connected by bonds that can flex. The flexing happens on tiny timescales. The imprint lasts in the spectrum over the whole transit. The second payoff arrives from why bands have internal texture. Molecules do not absorb just one way. They can rotate and they can vibrate. A vibration changes the spacing of atoms. A rotation changes orientation. Together they create clusters of lines around a central band. In a calm spectrum, these clusters can resemble a comb with uneven teeth. The visual anchor deepens as the ribbon is now seen under a gentle magnification. A broad valley is not smooth anymore. It contains faint ridges and shoulders. The shoulders rise and fall slowly. The ridges sit closer together. This is the fingerprint. It is not a name tag. It is a structure that can be compared across wavelength. Another payoff follows from the comparison itself. When multiple bands match the same molecule, confidence grows without any single line needing to be perfect. The analogy stays natural and quiet. Imagine ripples on a still pond after light rain. Each drop makes a ring. Different drops land at different places. Where rings overlap, a pattern of peaks and troughs appears. A single ring could be mistaken for something else. A repeating set of rings with consistent spacing is harder to dismiss. Molecular bands behave like those repeating ripples across wavelength. The pattern is the message. The visual anchor shifts to the limb again. The planet crosses the star. The atmospheric rim is thin. In certain colours, the rim looks slightly thicker. In neighbouring colours, it relaxes downward. These alternating lifts and relaxations are the band's footprint in geometry. The spectrum converts that into depth. The payoff is calm but sharp. The limb does not need to be resolved as an image. The wavelength dependence is enough to reveal the absorber. Now, a deeper layer of nuance enters still within a small set of concepts. Different molecules can share similar band regions. Overlap can occur. Two fingerprints can lie on top of each other. In that case, the spectrum is like two sets of ripples meeting. Some peaks align, some cancel, some distort. The result can look like a new pattern that neither molecule makes alone. The third payoff is that overlap is not purely a problem. It can be used. If a suspected molecule predicts a band that must appear elsewhere, that second band becomes a test. If it does not appear, the first match may be an accident of overlap. The spectrum becomes a self-checking landscape. The physical details supporting this check are steady. The limb samples different heights at different opacities. Strong parts of a band rise to thinner air. Weak parts dip toward denser layers until a cloud lid or continuum opacity stops them. This means a single molecule can show itself at multiple effective altitudes. That multi-altitude behavior can distinguish it from another molecule with a similar central band but different wings. The visual anchor returns to the ribbon landscape. A wide ravine appears at one region. Farther along, a second ravine appears with a related shape. The slopes have similar curvature. The floor has similar subtle ridges. The two ravines are separated in wavelength, yet they feel like the same hand carved them. That feeling is the fingerprint. Now the limit of observation arrives softly with a clear statement of what fails. Spectral resolution limits the ability to see the ridges inside a band. If colours are averaged too broadly, the comb texture becomes a smooth trough. Two different molecules can then look similar. Another limit comes from noise and baseline drift. A shallow band can be lost if the continuum is uncertain. A slope caused by scattering can hide the true depth of a band. The measurement is indirect and subtractive. It relies on tiny differences between in-transit and out-of-transit light. Any small mismatch can imprint a false motif. The payoff of admitting this is again practical. Bands that repeat in multiple regions and retain the same relative shapes are less likely to be false. Bands that appear only once and vanish when the baseline shifts are treated as uncertain. The mind stays calm because the method has internal redundancy. Another limit sits in temperature and pressure. The same molecule changes its band shape when collisions increase or when thermal motion broadens lines. A fingerprint is not a rigid stamp. It is a flexible one. This flexibility can confuse identification if not expected. Yet it can also inform it. A band that is wider than expected hints at deeper, denser layers contributing. A band that is sharper hints at higher, thinner layers dominating. The spectrum therefore carries both identity and condition. The scale shift widens without hurry. The internal motions of a molecule occur faster than a blink. The same molecule can persist in an atmosphere for long spans. Over those spans, mixing and chemistry can alter abundance. The transit captures a moment. The fingerprint is a snapshot of composition layered through height. The visual anchor becomes a slow sweep along the limb at the terminator. The rim thickness breathes with wavelength. It swells where bands are strong. It thins where windows open. The motion softens the concept. The fingerprint is not a chart. It is a changing boundary in silhouette. The next step is to understand why the same fingerprint can stretch and blur under different pressures and temperatures, and how that blur can be read rather than feared. A familiar fingerprint can soften until it barely looks like itself. Temperature and pressure reshape spectral lines, turning crisp marks into wider shadows. In that region, the atmosphere is a moving gradient rather than a fixed stamp. The limb is where this reshaping becomes visible. The slant path samples thin air and denser air together. Each layer contributes its own version of the same band. The first payoff is calm and direct. A broad feature often points to deeper, higher pressure layers contributing. A narrow feature often points to higher, lower pressure layers dominating. The visual anchor settles on a single absorption valley in the spectrum. At first it looks clean, then its edges become soft. The valley has wings that spread outward. The floor is not flat. It has a gentle curvature like sand that has been brushed by slow wind. This shape is not decoration. It is the physics of collisions and motion. A new term can enter once, and then fade. Pressure broadening is line widening from frequent molecular collisions. One sentence definition holds. Two example sentences follow. In dense air collisions, interrupt absorption and smear each line wider. In thin air, fewer collisions allow sharper lines to remain. One sentence completes the loop. This is why the same molecule can look different at different depths. A second reshaping comes from heat. Warmer gas has faster molecular motion. Faster motion spreads absorption across nearby wavelengths. The result is another kind of widening. It is gentle and symmetric in feel. The band becomes less like a notch and more like a shallow bowl. The physical detail is always present at the limb. Density drops upward. Temperature can change with height. Pressure drops quickly. These gradients mean the same band is built from many microenvironments. The spectrum is a sum of them. Another payoff follows from this layering. The core of a band tends to sample higher layers because it is most opaque. The wings tend to sample deeper layers because they are less opaque. This creates a quiet vertical reach inside a single feature. The band is a ladder whose rungs are blurred. The visual anchor shifts from the spectrum ribbon to a cross-section of the terminator. A thin atmospheric arc hugs the planet. Above the air is rare. Below the air is thick. The boundary where the band becomes opaque sits at one height in the core. It sinks lower in the wings. The core and wings therefore trace different rings around the limb. The same molecule appears as multiple nested boundaries. The analogy holds the idea without strain. Imagine a candle seen through layered fabric. A tight weave blurs the flame into a soft glow. A loose weave keeps a sharper point of light. Looking through stacked layers at a grazing angle mixes both effects. The shape of the glow carries information about the weave density along the path. In transmission, the weave is pressure and temperature. The glow shape is the band profile. The next payoff arrives from why this matters for false certainty. A band that is broader than expected can be misread as a different molecule. A band that is narrower than expected can be mistaken for noise. Recognizing broadening keeps identity from drifting. It also keeps the temperature story honest. A strong absorber at high temperature can produce a wide feature. The same absorber at lower temperature can look tighter. The spectrum does not only name gases, it also hints at conditions. The visual anchor returns to the absorption valley. Its shoulders slope slowly. The wings extend outward. The extension can be about a few tens of wavelengths bins wide, like a stain spreading across several boards of a pale wooden floor. The number is not important in itself. The everyday comparison is. The stain is wider than the original drop because the surface helps it spread. In the atmosphere, motion and collisions help lines spread. Another payoff follows from the shoulders. The slope of the shoulders can indicate the balance between thermal motion and collisions. A steep shoulder can imply thin upper layers dominate. A gentle shoulder can imply deeper layers contribute. The concept remains within a small set. It is line broadening. It is layered contribution. It is the core and wings probing different depths. Now the limit of observation arrives stated softly and precisely. Limited spectral resolution can blend the core and wings into one smooth trough. When that happens, the diagnostic shoulders disappear. The band becomes a single rounded dip. Different physical conditions can then look nearly identical. Another limit comes from clouds and hazes. A cloud lid can cut off the deeper layers that would have produced broad wings. The band can look artificially narrow, even if pressure broadening exists below. The spectrum can then mislead if the lid is not considered. This is a limit in inference rather than in physics. The measurement is indirect. It sees only the layers that light can traverse. The payoff of naming the limit is again stability. If wings are missing, it may mean clouds. If wings are present, it may mean deeper reach. The band shape becomes a test of access. The scene stays calm by returning to the limb's geometry. The grazing path is long. Upper layers are thin but extended. Lower layers are dense but can be hidden. The band core forms high. The band wings form lower. The planet's apparent radius shifts upward in the core. It shifts less in the wings. The difference between these shifts is a quiet signature of vertical structure. The scale shift widens without hurry. Inside a molecule, a line is shaped by collisions that last far less than a heartbeat. Those collisions happen countless times in a thin volume of gas. The cumulative effect becomes a smooth trough in a spectrum measured over a transit lasting hours. The atmosphere itself evolves over far longer spans, reshaping temperature profiles through time. Yet the band still carries the momentary imprint of that profile. Another payoff follows from time's calm roll. Repeated transits can reveal whether a band shape stays stable. If broadening changes, it may indicate changing temperatures or moving clouds. If broadening stays steady, it supports a consistent atmosphere. The visual anchor shifts to a slow sequence of transits. The planet crosses. The limb ring forms. The spectral valley appears with the same shoulders each time. The repetition makes the trough feel solid. The final portion settles into a gentle preparation for what comes next. Once broadening is understood, a fingerprint can be trusted even when softened. The next step is to face the masks that flatten spectra. Clouds and hazes can erase wings and hide cores. The spectrum then becomes a quieter surface. The journey continues by learning how that surface forms and how hidden layers can still be inferred. A spectrum can turn almost smooth even when the air below is complex. Clouds and hazes often act like a ceiling that hides deeper absorption, while leaving only a thin upper story visible. In that region, the limb is still a gradient, but the gradient meets a curtain of particles. The curtain is not a wall. It is a layer where opacity rises quickly across many wavelengths. The first payoff is clear. A flat transmission spectrum can mean a masked atmosphere rather than an empty one. The visual anchor opens on the terminator wrapped in a pale belt. The belt follows the curve of the planet like a soft ring. Its upper edge fades into thin air. Its lower edge looks denser and more uniform. Light behaves as a pathfinder that tries to dive deeper. It is turned back by the belt. The belt sets an effective radius that barely changes with wavelength. Molecular bands that would have lifted the limb boundary are muted. The atmosphere still exists. Its voice is simply softened. A new term can enter once and then soften away. A cloud deck is a particle layer that becomes opaque across a wide range. One sentence definition holds. 2 example sentences follow. If the deck sits high, deeper gases cannot imprint their bands. If the deck sits low, bands can still rise above it and remain visible. One sentence completes the loop. The cloud height decides how much of the spectrum becomes readable. The physical detail is the particle field itself. It has grains or droplets. It has size distribution. It has a vertical thickness. It can be patchy along the limb. The layer creates a boundary that is optical rather than solid. The boundary can look sharp in effect, even if it is gradual in density. The second payoff arrives from the way particles differ. Large particles tend to block light almost equally across colour. Small particles tend to scatter shorter wavelengths more strongly. This difference can turn a flat spectrum into a gentle slope. The slope is not a molecular fingerprint. It is a texture imposed by scattering. The visual anchor deepens. The belt around the terminator is now seen with a faint glow at its upper edge. The glow is not emitted light. It is scattered starlight redirected along the limb. The glow is stronger on the short wavelength side. It is weaker on the long wavelength side. This unevenness becomes a tilt in the spectrum. The payoff is immediate. A sloped continuum can point to haze even when molecular bands are quiet. The everyday analogy holds the contrast without strain. Imagine a frosted window with a thin film of dust. Large grains make the window simply dimmer. Fine powder makes the window look bluish and more diffuse near bright edges. The view behind the window can still be there. The film decides how much detail survives. In transmission, the view behind is the deeper atmosphere. The film is clouds or haze. The band shapes are the details that can be erased. The visual anchor shifts to the spectrum ribbon. Valleys that were once distinct are now shallow. The ribbon looks almost straight in places. In some regions, it tilts gently. The tilt is smooth, not structured. The payoff follows from smoothness. Smooth trends usually belong to broad particle scattering or broad opacity sources. Structured dips usually belong to molecules. When structure disappears but smoothness remains, particles are a strong suspect. Yet the calm story does not stop there. Particles can also mimic structure in subtle ways. If particle composition has its own absorption, features broad bumps can appear. If the haze thickness changes with height, curvature can appear. The limb becomes a layered fog bank with texture. The physical detail returns to the terminator cross-section. Below the haze, the air is denser. Above it, the air is thin and clearer. The optical boundary is near the haze top. The slant path spends most of its time near that boundary. The deeper layers contribute less because light is already blocked. This explains why the spectrum becomes insensitive to deeper composition. The next payoff is about what remains measurable. Even with a haze, the scale height above the haze can still be inferred from the residual variation. The haze does not erase all information. It changes which information is accessible. Now the limit of observation arrives softly and precisely. Clouds create a degeneracy between abundance and visibility. A weak molecular band can mean low abundance. It can also mean high clouds hiding the depths where the band would form. Without an independent measure of cloud top pressure, the spectrum alone may not distinguish these cases. Another limit comes from patchiness. If clouds cover only part of the limb, the observed spectrum is a mixture of clear and cloudy chords. The mixture can mimic a different cloud height or a different composition. The limb is not a single line. It is a ring, and different sectors can behave differently. The payoff of stating the limit is calm strategy. Features that change between transits can indicate patchy clouds moving. Features that stay stable can indicate a more uniform deck. The spectrum becomes a weather clue, but only indirectly. The scale shift widens without hurry. A haze particle can be smaller than a grain of smoke. A cloud deck can span thousands of kilometers around the terminator. The spectrum integrates both scales into a single curve. The curve is measured during a transit lasting hours. The processes that create hazes can operate over days or months. The long-term balance between formation and settling can reshape the deck over ages. Yet the measurement is a moment. It is a silhouette of a transient boundary. The visual anchor returns to the pale belt. It thickens slightly toward higher altitude. It thins slightly toward lower altitude. The edge of the belt is a gradient, not a step. In some colours, the belt looks more opaque. In others, it looks slightly more transparent. The spectrum records this as a gentle rounding of the continuum rather than sharp bands. The payoff follows from that rounding. The shape of the continuum can constrain particle size and altitude even when molecules remain hidden. A flat line suggests large particles or an optically thick deck. A tilted line suggests smaller particles and significant scattering. Both cases change the path light takes. Both cases reshape which layers speak. The final portion settles into preparation for the next mechanism. Scattering itself can imprint strong wavelength trends even without a thick cloud deck. Tiny particles can create a slope that competes with molecular bands. The next step is to understand scattering as a physics of direction. The limb becomes a place where light is not only absorbed, it is also redirected in quiet, systematic ways. A gentle blue tilt can appear even when no new molecule is present. Scattering reshapes the spectrum by redirecting light rather than absorbing it. In that region, the limb becomes a place of angles and tiny deflections. Light does not only pass through, it also bounces away from the straight path. The first payoff is clear. A smooth slope across wavelength can arise from particles alone. The visual anchor opens on the planet's terminator with a thin mist above it. The mist is faint. It is most visible where the stellar light grazes the edge. A narrow halo appears like a soft outline. The outline is brighter at shorter wavelengths. It fades at longer wavelengths. This is not emission. It is scattered starlight that is redirected into different directions. Light behaves as a stream that meets countless small obstacles. Each obstacle nudges the stream by a tiny angle. A new term can enter once and then soften away. Scattering is light changing direction after meeting particles or molecules. One sentence definition holds. 2 example sentences follow. Tiny particles tend to scatter short wavelengths more strongly. Larger particles scatter more evenly across colour. One sentence completes the loop. This is why scattering can draw a slope that is smooth rather than banded. The physical detail is in the way the limb looks layered. The upper haze is thin but extensive. The lower air is denser but less visible in the halo. The halo's brightness changes with height because density changes. It also changes with wavelength because scattering efficiency changes. The spectrum records this as a continuum trend. The second payoff arrives from the simplest case. If small particles dominate the short wavelength end rises in apparent radius, the planet looks slightly larger in blue light. It looks slightly smaller in red light. This is because blue light is scattered away from the direct path more readily. The limb becomes opaque higher up for blue. The effect can be about a few scale heights from blue to red, like a shoreline moving up and down across a low beach as tides change. The number is not the focus, the image is. A small vertical shift becomes a noticeable trend across the spectrum. The visual anchor deepens into the spectrum ribbon. Instead of distinct valleys, the ribbon leans. It climbs gently toward the short wavelengths. It relaxes toward the long wavelengths. The lean is smooth. It has no repeating pattern. This smoothness is the clue. Molecules carve structured ravines. Scattering paints gradients. Another payoff follows from combining the two. When a molecular band sits on top of a scattering slope, the band's depth can be misread if the slope is treated as a flat baseline. A band may seem shallow because the continuum is already rising. A band may seem deep because the baseline is tilted the other way. Recognizing scattering first stabilizes the interpretation of molecules. The analogy holds the sensation without strain. Imagine a beam of sunlight passing through dusty air in a quiet room. The beam looks brighter and bluer near the source. Farther along it looks dimmer and warmer. The dust does not add a pattern of stripes. It adds a soft wash and a change in colour balance. In transmission, the limb haze plays the role of dust. The starlight beam is the grazing chord. The spectrum is the colour balance of that beam after its long passage. The visual anchor shifts back to the terminator cross-section. A thin haze layer sits above the deeper atmosphere. The haze is made of particles small enough to float high. Below larger particles may settle. The boundary between them is not sharp. It is a gradient where size and abundance change with height. Scattering is strongest where small particles are most abundant. That is often higher up. The payoff is immediate. A steep scattering slope points to high-altitude small particles. A flatter slope points to larger particles or a thicker deck that blocks the view before scattering dominates. Now a deeper nuance enters while keeping concepts few. Scattering is not always purely from particles. Molecules can scatter as well. In very clear atmospheres, molecular scattering can create a slope, even without haze. This slope is usually gentler. It depends on density and wavelength. The limb then becomes a clear glass edge rather than a dusty veil. The spectrum still tilts, but in a quieter way. The limit of observation arrives softly here with a clear statement. A smooth slope is easy to mistake for instrumental baseline drift. It is also easy to confuse with uncorrected stellar colour variations. The measurement relies on comparing in-transit and out-of-transit light with high stability. If the baseline changes with time or wavelength, it can mimic scattering. Another limit sits in the degeneracy between particle size and abundance. A small number of very small particles can create a slope. A larger number of slightly larger particles can create a similar slope. Without additional information, the spectrum alone may not pick a single solution. The payoff of naming the limit is calm strategy. The slope is tested by its consistency across multiple wavelength ranges. It is tested by whether molecular bands sit on top in a coherent way. It is tested by whether the same trend repeats across transits. The scene stays steady by returning to geometry. Scattering removes light from the direct path. In transmission, that removal looks like additional opacity. It lifts the effective rim. The lift is stronger where scattering is stronger. The effective rim becomes a wavelength-dependent contour line. This makes scattering a sculptor of the continuum. Another visual anchor arrives in the form of a faint aureole around the planet's limb. The aureole is most apparent near the start and end of the transit. The grazing angles are most extreme there. The aureole thins as the planet moves inward across the stellar face. This change reminds that geometry matters. The same haze can have different optical impact depending on the chord. The payoff is gentle. Timing and wavelength together can help separate scattering from absorption. Scattering tends to act smoothly and broadly. Molecular absorption tends to act in structured bands. The scale shift widens without hurry. A particle can be smaller than a grain of smoke. Its interaction with light is a dance of electromagnetic waves happening in moments. The collective effect of countless particles around a planet shapes the appearance of the entire world during a transit. That appearance is measured over hours. The haze itself can be replenished or removed over longer spans. Winds can loft particles, settling can clear them, chemistry can create new aerosols. Yet the spectrum captures the quiet balance at one alignment. The final visual anchor returns as the spectrum ribbon. The slope is now seen as a background hill. On that hill, faint molecular valleys may appear. Reading the valleys requires knowing the hill's shape. The next step is to meet the hardest kind of confusion. False positives can arise when different causes produce similar dips or slopes. The journey continues by learning how to recognize imposters without losing the calm signal. A convincing dip can appear without any molecule causing it. False positives often arise when different effects paint similar shapes onto the same thin spectrum. In that region, the limb remains a quiet arc, but interpretation becomes the fragile part. A single trough can be made by a gas band. It can also be made by a mismatch in baselines. It can be made by patchy clouds mixing clear and cloudy chords. The first payoff is immediate. A true feature usually repeats in a coherent family, while an imposter often fails a second test elsewhere. The visual anchor opens on two spectral ribbons laid side by side like twin streams. Both have a shallow valley at the same place. One valley belongs to the planet's air. The other belongs to a subtle distortion in the reference light. At first glance, they look identical. The difference is in how they connect to the surrounding slope. Light behaves as subtraction, and subtraction can inherit any small inconsistency. A new term can enter once and then soften away. A false positive is a feature that mimics a real atmospheric signal. One sentence definition holds. Two example sentences follow. It can come from noise patterns that align by chance. It can come from systematic trends that look like smooth absorption. One sentence completes the loop. The reason it matters is simple. A single mistaken identification can reshape the entire atmospheric story. The physical detail stays rooted in the transit geometry. The planet blocks a chord across the star. The limb filters light along a ring. The signal is extracted by comparing in-transit to out-of-transit brightness at each wavelength. If the comparison is imperfect, the residue can look like absorption. The second payoff arrives from a practical safeguard. Real molecular absorption tends to appear in multiple places with related shapes. If one band is present, another band is often expected at a different wavelength range. The spectrum becomes a set of cross-checks. A lone dip with no companions is treated gently, not embraced. The visual anchor deepens into the spectrum landscape. A valley appears. Farther along the ribbon stays flat when a companion valley would be expected. That absence is information. It does not prove emptiness. It restrains certainty. Another kind of imposter comes from the mixture of limbs. Clouds can be patchy. One sector of the terminator can be clear, another can be veiled. The observed spectrum becomes an average of two different limb boundaries. This average can create a feature that resembles molecular structure, especially when the clear path reveals deeper bands and the cloudy path suppresses them. The mix can yield a shallow dip that looks stable. The payoff is immediate. A mixed limb can imitate a low abundance when the true cause is partial coverage. The visual anchor shifts to a planet's rim seen as a full ring. One half looks slightly hazy, the other half looks clearer. The haze has a soft edge, it does not stop abruptly. The clear half has sharper molecular relief. When combined, the ring becomes a compromise. The spectrum becomes a blurred blend. The analogy holds the blend without strain. Imagine two sheets of patterned glass laid on top of each other. One sheet has faint waves, the other is nearly smooth. Stacking them produces a new pattern that neither sheet alone shows. The new pattern is not a new material. It is an average of two states. In transmission, patchiness creates the same kind of emergent pattern. Another payoff follows from time. If patchiness changes, the emergent pattern changes. A real molecular band tied to global composition should remain consistent across repeated transits within noise. A patchy cloud pattern can drift. It can change the apparent depth of features without changing their central positions. The spectrum becomes a quiet indicator of stability. The visual anchor becomes a sequence of transits, each one a slow crossing. The planet's silhouette repeats. The rim note repeats. In one crossing, a shallow dip is slightly deeper. In the next, it is slightly shallower. The change is not dramatic. It is a whisper of variability. Now another imposter enters still within a small set of concepts. The continuum slope from scattering can be mistaken for a broad molecular band. A wide trough with no clear structure can tempt a chemical label, yet broad slopes often arise from particles. The payoff is a gentle rule. When structure is missing, particle explanations are considered first. This keeps chemistry from being invented out of smoothness. The physical detail is the spectral slope itself. It is a gradient, not a notch. It spans a wide wavelength range. It is anchored to the limb's scattering halo rather than a discrete band. The limit of observation arrives softly and precisely. Low signal to noise can align random fluctuations into a pattern that looks meaningful. The mind is skilled at seeing shapes in noise. Another limit sits in correlated noise. Errors can be similar across neighbouring wavelengths because of shared systematics. That correlation can create a false band-like trough. The spectrum then carries a memory of the measurement process. It is not pure atmosphere. The payoff of naming this limit is a calm method. The feature is tested by changing how the data is divided in time. If the dip appears only in one segment, it may be a transient systematic. The feature is tested by looking for the same dip in other transits. If it does not return, it is treated as uncertain. The feature is tested by seeking a companion band. If no companion exists where one should, the identification is held back. This is not harsh skepticism. It is gentle discipline. The scale shift widens without hurry. The absorption signature begins at a molecular scale. It becomes a millimetre-thin change in relative brightness on a spectrum ribbon. That ribbon then supports claims about a whole atmosphere spanning thousands of kilometres in circumference. Over long time, such claims feed into models of climate and loss. A single false positive can therefore echo across a large ladder of inference. The calm approach keeps each rung firm before stepping higher. The visual anchor returns to the twin ribbons again. One ribbon is smoothed slightly and the valley fades. The other retains a coherent family of valleys across the spectrum. The contrast is quiet but decisive. The imposter feature is lonely. The true feature has relatives. The section settles into a soft transition. The next challenge is even more subtle because the star itself can imprint false colours. The surface of the star is not uniform. Its texture can leak into the transmission spectrum unless carefully separated. The journey continues by drifting from planetary limbs to stellar limbs, and then back again with patience intact. A star's surface seems smooth until a transit makes its texture matter. Stellar spots and bright regions can imprint colour changes that masquerade as planetary atmosphere. In that region, the planet's shadow crosses not a uniform disk, but a mottled field of brightness. The first payoff is straightforward. A spectrum can inherit the star's patchwork if the blocked light is not representative of the whole star. The visual anchor opens on the stellar disk as a soft circle with subtle shading. The edge is dimmer, the centre is brighter. Across the face, darker patches sit like ink stains in paper. Nearby, brighter patches sit like pale scuffs that catch more light. The planet begins its slow crossing. Its silhouette is clean. Its path grazes a darker patch. The total light drops. The drop is slightly different in colour because the patch has a different spectrum than the rest of the star. Light behaves as a blend from many surface regions. During transit, a small piece of that blend is removed. If the removed piece has different colour, the remaining blend shifts. A new term can enter once and then soften away. Stellar contamination is stellar surface features altering the inferred planetary spectrum. One sentence definition holds. 2 example sentences follow. If a dark spot is unocculted, the star looks redder overall. If a bright region is unocculted, the star looks bluer overall. One sentence completes the loop. The planet then appears to have a slope or band that belongs to the star instead. The physical detail is in the star's limb and patches. Limb darkening is a gradient. The outer edge is dimmer because light emerges from cooler, shallower layers at grazing angles. Spots are cooler regions, they are darker. Bright regions are hotter or magnetically altered areas, they are brighter. Each has its own spectrum. When the planet blocks a chord, it samples a particular mix of these components. The second payoff arrives from a common trap. If the star has unocculted dark spots, the out-of-transit light is slightly dimmer and redder than a spotless star. The transit depth is measured relative to that baseline. The planet then seems larger in blue light than it truly is. That false slope resembles scattering in a planetary haze. A spectrum can therefore show a blue tilt that is not atmospheric. The visual anchor deepens into a pair of transit silhouettes. In one, the planet crosses a quiet region. In the other, the planet crosses a spotted belt. The silhouettes look the same, yet the colour-dependent depths differ. The difference is small. It's like a faint smudge on a clean mirror. It matters because transmission signals are small. Another payoff follows from timing across the transit. A spot crossing can create a localized bump in the transit shape. That bump can be a clue that the planet occulted a spot. When such bumps exist, the data may reveal the stellar patchwork directly. When bumps do not exist, unocculted spots can still bias the spectrum silently. The absence of a bump is not proof of a spotless star. The visual anchor shifts to a slow-moving shadow line across the stellar face. The shadow passes near a dark patch but does not fully cover it. The patch remains unocculted. It contributes to the baseline. The planet's blocked light comes from a brighter region nearby. The baseline is redder than the blocked chord. The resulting differential creates an artificial blue slope. The analogy holds this without strain. Imagine measuring the tint of water by dipping a ladle from the surface. If the bowl has a darker stain on one side, the overall watercolour appears darker. A ladle taken from the clean side seems brighter by comparison. The method then infers a tint difference that comes from the bowl, not the water. In transit, the bowl is the star's surface. The ladle is the blocked chord. The planet's atmosphere can be blamed for a difference caused by the stellar background. Another payoff appears when considering bright regions. Bright patches can bias the spectrum in the opposite direction. If unocculted bright regions make the star bluer, the planet can appear to have a redder slope than it truly does. This can mimic reduced scattering or different particle sizes. It can also distort molecular band depths by changing the baseline. The physical detail stays clear. The stellar disk is not uniform. It is a sum of regions with different temperatures. Those temperatures change the emergent spectrum. The transmission spectrum is then a ratio of 2 stellar spectra rather than a pure planet signature. Now the limit of observation arrives softly and precisely. Stellar surface patterns cannot be fully resolved from transit data alone. The spectrum provides indirect evidence, not direct maps. Many different spot distributions can yield similar color biases. Another limit sits in time variability. Spots evolve. They rotate in and out of view as the star turns. A baseline measured on one day may not match another day. If transits are combined across long spans, stellar variability can create artificial features or wash out real ones. The payoff of stating the limit is calm method. Consistency checks become essential. A suspected atmospheric slope is compared across epochs. If it tracks stellar brightness, changes suspicion increases. If it remains stable while the star varies, confidence grows. Another method is spectral self-consistency. Stellar contamination tends to be smooth with wavelength, though it can have broad features tied to stellar spectral lines. Planetary molecular absorption tends to appear in band families. This difference can help, but it is not absolute. The limb of the star introduces its own complication. Limb darkening depends on wavelength. The planet blocks different limb angles as it moves. That can create color-dependent shapes in the transit curve. If limb darkening is modeled imperfectly, residuals can look like shallow absorption. The physical detail is a gradient across the stellar disk. The center is bright. The edge is dim. The gradient is stronger in some colors than others. The planet samples this gradient as it traverses chords. A small modeling error can bias the depth. The payoff is again practical. Features that depend on transit chord geometry are treated with caution. Features that persist across different chords can be more reliable. The scale shift widens without hurry. A star spot is a region thousands of kilometers across. It is still tiny against the star. The planet's silhouette is also tiny against the star. The spectrum is built from the difference between two huge fluxes. Yet that tiny difference is used to infer molecules that exist on scales smaller than a grain of smoke. The ladder of inference is long. Each rung must be stable. The visual anchor returns to the mottled star. The planet's dark disk slides across. It blocks a bright patch for a while, then a more ordinary region. The inferred spectrum changes slightly with that path. The calm lesson settles. The star is not merely a backlight. It is part of the signal. The next step is to learn how time and repetition can separate stable planetary features from drifting stellar texture. Multiple transits can be stacked like quiet layers until the planet's consistent imprint remains. A faint atmospheric imprint becomes clearer when many quiet crossings are placed together. Repetition separates stable planetary structure from drifting noise and stellar texture. In that region, time acts like a gentle filter rather than a force. One transit is a whisper. Many transits become a steady tone. The first payoff is direct. Random fluctuations fade when they fail to repeat at the same wavelengths. The visual anchor opens on a sequence of transits as a slow parade of silhouettes. Each crossing draws the same dark disk across the same bright face. The limb ring appears each time as a thin inferred outline. In some colors, the outline lifts. In others, it sits lower. Each transit adds another faint layer to the same pattern. Light behaves as an accumulation of differences. A signal would persist where physics is stable. Noise would wander. A new term can enter once and then soften away. Stacking is combining multiple observations to improve clarity. One sentence definition holds. Two example sentences follow. When patterns are aligned, repeated features reinforce each other. When patterns are unaligned, their average tends towards zero. One sentence completes the loop. This is why repetition is not just more data. It is a test of reality. The physical detail remains the transit curve itself. The planet's shadow has a smooth ingress. It has a flat bottom. It has a smooth egress. Within that smoothness, tiny wavelength-dependent differences exist. They are shallow. They can be about 1 part in 10,000, like a single grain of pepper seen against a pale plate. The number is modest. It explains why stacking is needed. The second payoff arrives from how stacking improves the spectrum. Noise often varies from one transit to the next. Baseline drifts can change. Small calibration offsets can shift. When many transits are averaged, those changes blur out. The stable wavelength-dependent limb shifts remain. The spectrum becomes less ragged. The valleys become smoother. The slopes become more trustworthy. The visual anchor deepens into the spectrum ribbon. Early on, the ribbon is jagged. It has little teeth that rise and fall. After many transits, the teeth soften. A few broad shapes remain. A set of valleys repeats with consistent spacing. The continuum slope steadies. The payoff is immediate. A repeating family of bands becomes visible without any single transit needing to be decisive. Now a deeper checkpoint appears. Stacking is not merely averaging, it is aligning. The transits must be matched in time and wavelength. The planet's path across the star must be comparable. If the chord changes, the stellar surface sampled can change. If the star evolves, the baseline can change. The method therefore asks for careful grouping. The visual anchor shifts to 2 stacks. One stack includes only transits with similar shapes. The other stack includes mixed shapes. The mixed stack produces a spectrum with odd curvature. The consistent stack produces a cleaner pattern. The payoff follows. Consistency in geometry increases confidence that the spectrum belongs to the planet rather than the star. The analogy holds the idea without strain. Imagine laying many thin tracing papers on a table. Each sheet has a faint drawing of a shoreline. Some sheets are shifted, some are rotated. If all are aligned, the true coastline darkens and becomes clear. If alignment is sloppy, the coastline smears into a fog. Stacking works the same way. Alignment is not a technical luxury. It is the difference between a fingerprint and a blur. The physical detail returns to timing. Ingress and egress define where the limb is most influential. Mid-transit defines where the chord samples a steady brightness field. If stacking mixes different timing offsets, the limb signal can smear. The result can look like a broader feature. It can look like a shallow slope. It can even create a false band. The payoff is practical. Time alignment protects against false positives created by smearing. Another payoff arrives from the distribution of noise. Some noise is random. Some noise is correlated across wavelength. Correlated noise can survive averaging if it repeats in a similar way. This is why stacking alone is not enough. The stacked spectrum must still be tested for coherence across expected companion bands. It must still be checked against independent wavelength regions. The visual anchor becomes a set of faint companion valleys that emerge together. When one valley deepens, another deepens in step. The pair acts like a lock and key. This coherence is difficult for noise to mimic across wide ranges. Now the limit of observation arrives softly and precisely. Stacking can also hide variability that is real. If the atmosphere changes from transit to transit, averaging can wash out features. Patchy clouds can shift. Hazes can thicken. The spectrum can vary. A stack would then produce a compromised spectrum that belongs to no single epoch. Another limit sits in stellar evolution. Spots can appear and disappear. Bright regions can drift. If those changes correlate with wavelength, a stacked spectrum can still retain a bias. The average would not remove a systematic that repeats with the star's rotation pattern. The payoff of naming the limit is calm method. Variability is tested by comparing subsets of transits rather than only the full stack. If a feature is present in each subset, it is more likely stable. If it appears in one subset only, it may reflect time-dependent clouds or stellar states. The visual anchor shifts to 3 separate stacks placed side by side like 3 calm ponds. Each pond has gentle ripples. In one pond, a valley is deeper. In another, it is shallower. In the third, it is absent. The comparison reveals that the valley is not fully stable. The payoff is quiet. Instability itself is information. It suggests weather or stellar change, and it guides caution in interpretation. The scale shift widens without hurry. A transit lasts hours. A spectrum is built from differences across those hours. Stacking gathers many hours into days of integrated time. Those days are still brief compared to atmospheric chemistry timescales. Over longer spans, atmospheres can lose gases, they can gain hazes, they can shift temperature profiles. The stacked spectrum is a snapshot of a period, not an eternal portrait. It is nonetheless powerful because it turns faintness into legibility. Another payoff arrives from the way stacking clarifies the next challenge. Once stable features emerge, attention can move from detection to explanation. The shape of each band can be measured. The continuum slope can be separated. The relative depths of bands can be compared. This sets the stage for retrieving physical parameters, but with humility. The spectrum remains an indirect view. It constrains families of atmospheres rather than a single answer. The visual anchor returns to the parade of transits. The silhouettes repeat with unhurried regularity. The limbering is inferred again and again. Over time, the same wavelength-dependent lifts remain. The noise that once looked like random teeth has settled into a smooth landscape. The section settles into a gentle transition. With a cleaner spectrum, chemistry and physics can be connected more tightly. The next step is to consider how mixing and non-equilibrium processes can create unexpected molecules above clouds. The journey continues by letting the spectrum hint at motion and chemistry that do not sit still. A calm spectrum can hint at chemistry that never quite settles. Equilibrium gives one expected mix, yet vertical mixing can preserve molecules where they should fade. At this distance, the limb is a thin cross-section of an atmosphere in motion. Layers stack by pressure and temperature. The spectrum samples those layers by opacity. The first payoff arrives in a simple distinction. Some molecules reflect local conditions, others reflect where they came from. The visual anchor opens on the terminator as a tall column of air. The column is imagined in soft layers. Each layer has a slightly different tint. A faint ribbon of gas rises through them. It is not a jet. It is a slow drift that bends with altitude. Light behaves as a probe of this column. It sees higher layers in band cores. It sees lower layers in band wings. The column becomes a quiet map of chemistry with height. A new term can enter once and then soften away. Chemical equilibrium is the mix favoured at a given temperature and pressure. One sentence definition holds. Two example sentences follow. In warm, deep layers, certain molecules are stable and abundant. In cooler upper layers, the same molecules would prefer to transform into others. One sentence completes the loop. When the spectrum shows a deep layer molecule high up, the atmosphere is likely not fully equilibrated. The physical detail is the gradient itself. Pressure drops upward. Temperature often changes with height. Density thins into a rare fringe. Within that fringe, reactions can slow. Collisions become less frequent. The chemical clock ticks more quietly. Another payoff follows from the idea of competing clocks. Mixing can move gas upward faster than reactions can resort it. The result is a preserved composition. It is not perfect. It is simply out of step with local equilibrium. The term can be named once and then left. Quenching is composition freezing when mixing outruns chemistry. One sentence definition holds. Two example sentences follow. A molecule formed deep down can be carried upward before it transforms. The upper atmosphere then contains more of that molecule than local equilibrium predicts. One sentence completes the loop. This matters because the spectrum may be reading deeper conditions through an upper layer shortcut. The visual anchor deepens. The rising ribbon in the column reaches a height where the air becomes thin. The ribbon spreads sideways into a gentle shelf. The shelf traces the limb like a faint band. The band has a clear upper boundary that fades. It has a lower boundary that looks sharper. This is the physical signature of mixing in a stratified atmosphere. It creates a layer where composition changes more slowly with height than expected. The next payoff arrives from a single safe number. The chemistry clock in thin upper layers can be about 1 day like a full cycle of a slow ocean swell. Mixing can be faster or slower. When mixing is faster than about 1 day, disequilibrium becomes more likely. The number is not a rule, it is a sense of scale. It links microscopic reaction rates to the macroscopic circulation of a whole planet. The analogy holds the competing clocks without strain. Imagine a canyon filled with stacked fog layers at dawn. Warm air rises along the slope. Cool air sinks into hollows. If the air shuffles faster than the fog can dissipate, the fog pattern persists in places it would not persist by stillness alone. The atmosphere behaves in a similar way. Chemistry is like fog forming and clearing. Mixing is like the slow breathing of air through the layers. The visual anchor shifts to the spectrum ribbon. A band appears where equilibrium would predict weakness. Its presence is steady. Its shape suggests an upper layer contribution. The band is not an isolated clue. It sits alongside a companion band that also persists. Together they suggest a shared origin in deeper layers. The payoff is immediate. A pair of unexpected bands is stronger evidence than a single odd dip. Now the section leans into the boundary of intuition. It is tempting to treat every detected molecule as local truth. The limb refuses that simplicity. The limb is a slant path through many heights. The detected abundance is an effective average. It blends layers where chemistry is fast with layers where chemistry is slow. It also blends clear sectors with hazy sectors. Another payoff follows from this blend. Disequilibrium can explain why some bands are stronger than expected without needing extreme abundances. A molecule can be moderate in deep layers. Mixing can lift it into the observable heights. The spectrum then sees it with amplified clarity because those heights contribute strongly to transmission. The physical detail stays grounded. The limb boundary rises where opacity is high. If a quenched molecule has a strong band, that band lifts the boundary in thin air. Thin air has long slant paths. Long slant paths magnify small opacities. A molecule carried upward can therefore dominate a spectrum even if it is not dominant by mass. The visual anchor returns to the terminator column. The rising ribbon now appears as a slow spiral. It follows the curvature of the planet. It fades into a higher haze layer. This spiral is not observed directly. It is an imagined guide to interpret the spectrum's vertical hints. The limit of observation arrives softly and precisely. A spectrum cannot directly measure vertical wind speeds. It infers mixing from composition patterns. Many different mixing strengths can fit the same bands if temperature profiles are uncertain. Another limit sits in reaction networks. Different chemical pathways can produce similar molecular sets. Without independent constraints, the spectrum may not distinguish whether a molecule is preserved by mixing or replenished by high-altitude chemistry. The payoff of stating the limit is calm humility. Disequilibrium is suggested by consistency across multiple molecules and multiple bands. It is supported when the same mixing picture explains several features at once. It is weakened when each feature requires a different story. The section stays within a small concept set. Equilibrium is the baseline expectation. Mixing and quenching are the mechanism of persistence. Disequilibrium is the outcome seen in bands. The scale shift widens without hurry. Reaction steps occur in times shorter than a blink. Mixing spans heights measured in dozens of kilometers. Those heights trace a ring around a planet thousands of kilometers wide. The spectrum compresses this entire ladder into gentle dips on a ribbon of light. Over longer spans, changing stellar irradiation can shift the equilibrium baseline. Over even longer spans, atmospheric loss can change the inventory itself. Yet the spectrum remains a snapshot of competing clocks at one alignment. The visual anchor settles again on the spectrum landscape. A few bands hold steady. Their relative depths align with a single mixing picture. The calm conclusion arrives without sharp edges. Chemistry in transmission is not only about what exists, it is about where it is allowed to remain. The next step is to look at specific molecule families and broad absorbers that overlap like layered shadows, and to learn how to separate them without haste. A spectrum can look simple while hiding several absorbers tangled together. Overlapping bands often blend into one broad shape. and that blend can mislead identity. In that region, the limb does not offer separate layers in isolation. It offers a summed silhouette. The first payoff is quiet and firm. When two gases absorb in the same wavelength neighbourhood, the spectrum may show only one combined dip. The visual anchor opens on a broad trough in the spectrum that has a gentle shoulder. The trough is not a clean valley. It is a basin with a sloped rim on one side and a flatter rim on the other. A small notch seems to sit inside the basin. The notch is real, or it is a coincidence. The eye cannot decide yet. Light behaves as a traveller through stacked shells. Each shell adds its own faint shadow. When shadows overlap, their edges blur into a single outline. A new term can enter once and then fade. Spectral overlap is different absorbers affecting the same wavelength region. One sentence definition holds. Two example sentences follow. A broad absorber can set a smooth floor. A narrower absorber can carve shallow dents on that floor. One sentence completes the loop. This matters because the combined outline may resemble a different molecule entirely. The physical detail remains anchored to the limb. The chord is long. The effective boundary rises where opacity accumulates. If one absorber dominates high up, it lifts the boundary early. If another dominates deeper down, it adds wings that appear only where light reaches lower layers. Overlap, therefore, mixes vertical reach as well as wavelength reach. Another payoff arrives from the way overlap alters confidence. A single band is rarely a single story. Companion bands are still the strongest test, yet overlap can hide companions too. A companion may exist but be drowned by a broad background. A companion may be present but shifted in apparent depth by clouds. This is why overlap is treated like a fog over the fingerprint. The visual anchor shifts from the spectrum to the limb cross-section. A pale haze sits high. Beneath it, two gas layers have different mixing patterns. Their boundaries are not sharp, they are gradients. One layer thickens slowly with depth. Another rises in a thin, high-altitude shelf. The slant path samples all of it. The resulting spectrum is a braid made from different heights. The analogy holds the braid without strain. Imagine a glacier with two kinds of translucent ice layered through time. One layer is clear and blue, another is milky and white. Light passing through the glacier emerges with a blended colour that depends on both layers. If the milky layer thickens, the blue seems to fade even if it remains present. If the blue layer deepens, the white seems less dominant. The layers are real. The blended appearance is what reaches the observer. In transmission, broad absorbers are the milky ice. Narrower bands are the blue veins. Another payoff follows from a specific overlap that is especially quiet. Some absorption does not come from a single molecule alone. It comes from collisions between molecules. The effect is broad. It has few sharp edges. A new term can enter once and then soften away. Collision-induced absorption is broad absorption created during molecular collisions. One sentence definition holds. Two example sentences follow. In dense layers, collisions are frequent and the effect strengthens. In thin layers, collisions are rare and the effect weakens. One sentence completes the loop. This matters because it can create a smooth trough that looks like haze or baseline drift. The visual anchor returns to the broad basin with the shoulder. The shoulder now has a possible explanation. The smooth floor can be collision-driven absorption from deep layers. The notch can be a molecular band from higher layers that survives above clouds. The payoff is immediate. A broad floor and a narrow notch can point to two different altitudes speaking at once. The physical detail is the band shape. The notch has a sharper curvature. The floor has a wide radius of curvature. The transition between them is gradual, like a shoreline that becomes a cliff only in one small segment. The main number is used once with a plane comparison. The effective boundary can shift by about 50 kilometers, like the height difference between a low plain and a tall mountain range. That shift can be driven by overlap. A broad absorber raises the whole rim. A narrow absorber adds small extra rises within it. The spectrum then shows depth changes that are not purely abundance changes. Another payoff follows from how overlap interacts with temperature. Warmer air broadens bands, cooler air narrows them. When overlap exists, broadening can cause two separate valleys to merge into one. A merged valley can be mistaken for a single absorber at higher abundance. The spectrum becomes a puzzle of shapes rather than labels. The visual anchor shifts to a second spectrum ribbon that covers a different range. Here, two small valleys appear where only one broad valley existed before. The separation is gentle, it is not dramatic. Yet it changes the interpretation. The payoff is clear. Wider wavelength coverage can unbraid an overlap by revealing bands that do not overlap elsewhere. Now the limit of observation arrives softly and precisely. Limited wavelength coverage can force overlap to remain unresolved. The spectrum may show only the merged region and miss the separating region. Another limit sits in spectral resolution. If the bins are wide small, notches are smoothed away. Overlap then looks more complete than it truly is. A third limit sits in model dependence. If an absorber is missing from the model, the fit may assign its shadow to another absorber. The result can be a confident but incorrect identification. The payoff of stating these limits is calm method. Overlap is tested by searching for independent windows where one absorber is strong and the other is weak. Overlap is tested by checking whether the same abundance explains multiple band families. Overlap is also tested by allowing broad background sources like collisions and haze to vary without forcing them to mimic narrow structure. The visual anchor returns to the limb and its layered gradients. The upper haze acts like a soft lid. The deeper collision-driven absorption acts like a dim floor. Between them, molecular bands add relief. The combined effect is a landscape. Some hills belong to one layer, some belong to another. The spectrum is the only visible ridgeline. It must be read with patience. The scale shift widens without hurry. A collision event lasts less than a blink. Countless collisions in deep layers build a broad continuum that spans large wavelength ranges. That continuum then influences the inferred height of an atmosphere that circles a planet. Over long spans, the balance between deep temperature and upper haze can shift. The spectrum would then change in subtle ways. Yet even in a single snapshot, overlap reveals that atmospheres are layered and coupled. The section settles into a gentle transition. Once overlap is handled, the remaining question is not only what gases exist, but what the atmosphere does with energy. The journey continues by drifting from individual bands toward the broader consequences of heating, cooling, and long-term stability. A transmission spectrum does not only name molecules, it hints at how energy moves through an atmosphere. The same band that identifies a gas also marks where starlight is absorbed and where heat can be trapped. In that region, the limb is a boundary between day and night. The boundary is also a boundary between heating and cooling. The first payoff is immediate. A molecule that absorbs strongly at certain wavelengths can warm the layers where the limb becomes opaque. The visual anchor opens on the terminator as a softly lit arc. The upper layers glow faintly in one color range and dim in another. A hazy lid sits above. Below, a clearer layer shows sharper band relief. The opacity boundary rises and falls like a slow tide as wavelength changes. Light behaves as selective pressure. It does not push on matter. It selects where energy is deposited. A new term can enter once and then soften away. Radiative balance is heating and cooling tending toward equality. One sentence definition holds. Two example sentences follow. If absorption dominates, temperature rises until emission increases. If emission dominates, temperature falls until absorption catches up. One sentence completes the loop. The spectrum is a partial map of where absorption is possible. It is also a hint about how the temperature profile might be shaped. The physical detail is the vertical layering. Temperature often decreases with height in a lower region. It may increase again higher up if strong absorbers intercept starlight above. That increase is a temperature inversion. The term can be named once and then left. An inversion is temperature rising with height in a layer. One sentence definition holds. Two example sentences follow. A high-altitude absorber can heat the upper atmosphere. The lower layers then receive less starlight and stay cooler. One sentence completes the loop. This matters because an inversion changes the altitude where bands form. It can change the apparent depths in transmission. Another payoff follows from the connection between opacity and height. Transmission senses altitude through the effective boundary. If an upper layer is heated, scale height can increase. The boundary becomes puffier. Bands can deepen even if abundance stays the same. The spectrum then contains a thermal fingerprint layered on top of a chemical fingerprint. The visual anchor deepens. The limb column is imagined as a set of pressure surfaces. They are like faint stacked contours. In one scenario, the contours are closer together. In another, they spread apart in a warm upper zone. The spectrum responds. Band cores rise higher. Band wings become broader. The change is subtle. It is persistent. The payoff is clear. Temperature and composition are entangled in transmission, and disentangling them is part of the reading. The analogy holds the entanglement without strain. Imagine a soft sponge soaked with dye. The dye represents molecules. The sponge's swelling represents temperature. If the sponge swells, the same dye spreads through a thicker volume. Looking through the sponge, the tinted path becomes longer. The tint deepens without adding dye. If the sponge shrinks, the tint can fade even if dye remains. The spectrum sees both the dye and the swelling at once. The physical detail returns to gradients and boundaries. A haze layer can act like a reflective ceiling. It blocks deeper bands by cutting off the slant path. It also changes heating by reflecting starlight or absorbing it. If the haze absorbs, it warms. If it reflects, it cools layers beneath. The spectrum can hint at haze by a muted set of bands and a smooth slope. That hint then feeds back into thermal interpretation. Another payoff follows from a single safe number. A modest temperature change of about 200 degrees can noticeably alter band shapes, like the difference between a warm afternoon and a cold night at high altitude. The number is not tied to a specific planet. It is an order of magnitude guide. It shows that temperature shifts do not need to be extreme to matter. The limb is sensitive. The spectrum is sensitive. The visual anchor shifts to a spectrum ribbon with two versions. One version has slightly deeper bands. The other has slightly shallower bands. The positions are the same. The difference is mostly amplitude. This is where temperature can hide. A warmer upper layer expands the limb. A cooler upper layer contracts it. Chemistry could be unchanged. The payoff is immediate. A change in depth is not always a change in abundance. It can be a change in atmospheric thickness. Now the limit of observation arrives softly and precisely. Transmission alone struggles to pin down temperature. It primarily measures relative changes in radius with wavelength. Many combinations of temperature mean molecular mass, and reference radius can fit the same spectrum. This is a degeneracy. The term need not be named. The idea is enough. Another limit sits in unknown cloud tops. If a cloud deck truncates the path, it can mimic a colder, thinner atmosphere by reducing band depths. Another limit sits in the baseline reference level. Without a solid surface, the 0 point is not obvious. The spectrum measures differences more easily than absolutes. The payoff of stating these limits is calm method. Temperature hints are strengthened when multiple bands of the same molecule are compared because different bands probe different heights. Temperature hints are strengthened when scattering slopes and band shapes are considered together because they respond differently to scale height. Temperature hints are weakened when only one band is available. The visual anchor returns to the terminator arc. Above it, a thin, warm layer glows faintly in its own emitted light, imagined as a gentle halo. Below it, the air is denser and darker. The opacity boundary for some wavelengths sits high in the warm halo. For other wavelengths, it sinks into the cooler region. The spectrum is the record of these two choices. The scale shift widens without hurry. Energy absorption happens at the level of photons meeting molecules. That microscopic exchange accumulates into heating across kilometers of atmosphere. It then influences circulation around a planet that turns through day and night. Over longer spans, the star's output can change. The planet's orbit can shift. The long-term thermal structure can evolve. Yet a single transmission spectrum can still whisper where absorption concentrates and where the limb becomes thick. The section settles into a gentle transition. With thermal effects in mind, the next step is to consider long-term consequences. Atmospheric escape and chemical erosion can reshape what the spectrum can ever show. The journey continues by drifting from present structure towards slow loss and lasting change. A spectrum is a present-tense glimpse, yet atmospheres live on long timescales. Escape and erosion can quietly rewrite what transmission can reveal. At this distance, the limb is not only a window, it is also a threshold where gas can thin into space. The first payoff is steady. A strong high-altitude absorber can both deepen a band and signal that the upper atmosphere is extended. The visual anchor opens on the night-side edge as a faint, swollen halo. The halo is not sharp. It has a soft outer boundary that fades into darkness. Closer in, the halo becomes denser and more defined. The planet's solid disk remains a clean silhouette. Above it, the gaseous outline looks like a mist that stretches farther than expected. Light behaves as a tracer of height. When the boundary rises at many wavelengths, the atmosphere appears puffed. A puffed atmosphere can be warm low in mean molecular mass or actively escaping. The physical detail is the gradient at the top. Density falls upward. The fall is not a cliff. It is a long taper that can extend into a very thin exosphere. In that thin region, particles can travel far between collisions. The atmosphere becomes less like a fluid. It becomes more like drifting grains. A new term can enter once and soften away. Escape is atmospheric gas leaving the planet for good. One sentence definition holds. Two example sentences follow. Light gases can leak away when thermal motion is high. Energetic radiation can also accelerate loss by heating the upper layers. One sentence completes the loop. This matters because escape changes composition over time. It can erase certain signatures and amplify others. Another payoff follows from a simple cause and effect. If hydrogen escapes more easily, the remaining atmosphere becomes heavier. A heavier atmosphere has a smaller scale height. A smaller scale height makes bands shallower. The spectrum can therefore quiet down as an atmosphere matures. This is not a single path. It is a tendency. The visual anchor shifts to two imagined epochs. In the earlier epoch, the halo is tall and bright in a few bands. In the later epoch, the halo is tighter and dimmer. The planet's silhouette looks the same. The limb ring changes. The payoff is immediate. Transmission is sensitive to evolution because it is sensitive to height. The analogy holds the slow loss without strain. Imagine a soap bubble resting in still air. At first, the film is thick enough to show strong colours. Over time, the film drains. It becomes thinner. The colours fade and shift. The bubble still exists for a while, yet its optical signature changes before it disappears. An atmosphere can behave similarly in spirit. Its visible imprint can change as the upper layers thin. The physical detail returns to the limb boundary. In escaping atmospheres, the boundary may not be described by a single pressure level. It may be influenced by an extended tail. The tail can be asymmetric. It can broaden on one side. It can create a longer ingress or egress in a specific band. The spectrum is not only about depth, it can also be about shape in time. Another payoff follows from how certain lines respond to escape. Some absorbers are strongest high up. They can trace the topmost layers where escape begins. If such a line deepens more than expected relative to others, it suggests an extended upper region. The suggestion is not definitive, it is a clue. The visual anchor becomes a time series of transit shapes in a single band. The transit is slightly wider in time than neighbouring bands. Its edges are softer. The planet seems to cast a larger shadow in that band alone. The payoff is clear. A wavelength-dependent widening can indicate an extended halo rather than only a deeper opacity in a compact layer. The main number appears once with an everyday comparison. Over about 1 billion years, like the time between distant geological eras on a rocky world escape, can significantly reshape an atmosphere. The number is a scale marker. It shows that slow change can matter. It also shows that present spectra are snapshots within a long movie. The scale shift widens gently. Individual particles move in fractions of a second. Collisions and chemistry adjust over hours and days. Atmospheric loss can accumulate over millions to billions of years. The spectrum compresses this range into a single curve. It is a quiet summary of a dynamic history. Now the limit of observation arrives softly and precisely. Transmission cannot directly measure escape rate from one spectrum alone. Many factors can mimic an extended halo. High temperature can puff the atmosphere without active loss. Low mean molecular mass can puff it as well. Hazes can also alter the apparent boundary in ways that resemble extension. Another limit sits in unknown stellar activity. Variable high-energy radiation can drive episodic escape. A single observation may catch a quiet phase or an active phase. Without repeated monitoring, the inferred state can be biased. The payoff of stating the limit is calm discipline. Escape claims become stronger when wavelength-dependent time-shape changes are consistent across multiple epochs. They become stronger when multiple species tracing high altitudes point to the same extension. They become weaker when only a single broad feature is available. The visual anchor returns to the halo and adds a physical texture. The halo has a denser inner rim. It has a fainter outer veil. The outer veil is almost invisible, yet it matters because it can contribute to absorption in narrow high-altitude lines. The boundary is therefore not one edge. It is a layered fade. Another payoff follows from the connection to false signals. A stellar bright region crossing can imitate a deeper band. A baseline drift can imitate a broadened transit. These are the traps that escape interpretations must avoid. The halo must be separated from stellar texture by consistency, and by comparisons across wavelengths that respond differently to stellar effects. The atmosphere is treated as a hypothesis tested against these alternatives. The visual anchor shifts to a pair of bands. One band is sensitive to high altitude, the other forms deeper down. In an escaping scenario, the high altitude band broadens in time while the deep band does not. This differential behavior is hard for a simple baseline shift to mimic. The payoff is immediate. Differences between bands act like a cross-check that does not require absolute calibration. The section settles into a wider perspective. Escape and long-term change do not erase the value of transmission. They deepen it. A spectrum can be read as present structure and as possible trajectory. A tall halo can imply youth or ongoing stripping. A compact limb can imply maturity or heavier composition. The journey is not about certainty. It is about narrowing stories that fit both physics and the observed shapes. The final transition arrives softly. With evolution in view, the last step is a gentle synthesis. The spectrum becomes a language of limits and possibilities rather than a catalogue. The next section eases toward a quiet resolution and a stable resting horizon. A thin rim of atmosphere can seem like a fragile detail, yet it carries a complete physical story. That story is read by watching starlight pass through a limb and come out changed. At this distance, transmission is a method of inference rather than a photograph. It does not show clouds directly. It shows how a boundary shifts with wavelength. The first payoff is simple and steady. A deeper dip at one wavelength means the atmosphere blocks light higher there. A shallower dip means the boundary sits lower. The visual anchor opens on a planet crossing a star in silence. The planet is a clean disk. Around the disk, a faint ring of air bends and filters the light. The ring is thicker on the side where haze rises. It is clearer where the gradient falls away. The ring is not uniform. It is layered with a soft outer veil and a sharper inner edge. Light behaves as a probe that skims long paths. It passes through the slant column. It is weakened by absorption. It is redirected by scattering. Two concepts remain in view without crowding. One is the idea of a spectral fingerprint. The other is the idea of a moving boundary set by opacity. Fingerprint can stay plain. Opacity can be held as a single word and then returned to imagery. The physical detail is the way bands form in layers. Band cores often form higher where the air is thinner. Band wings often form deeper where the column is denser. A spectrum is therefore not one height. It is a stack of heights. That stack can be disturbed by clouds. It can be stretched by warmth. It can be tightened by heavier gases. Another payoff follows from this layered view. Different features do not simply add information. They overlap in altitude. When two features agree on a shared shape, confidence increases without certainty becoming absolute. The visual anchor shifts to a ribbon of colours that drifts from blue to red. Across the ribbon, several valleys appear. One valley is narrow and deep, another is broad and shallow. The baseline slopes gently upward, as if a thin mist adds a soft tilt. The entire ribbon resembles a shoreline seen from far above. The shoreline is never perfectly straight. It curves with hidden sandbars. It is defined by how waves break. In the same way, the spectrum is defined by where light breaks against opacity. The everyday analogy holds the method without human scenes. Imagine a glacier with many thin layers of snow and dust. Each layer is a season pressed into ice. Looking along the side of the glacier, darker lines reveal periods of heavy dust. Clearer ice reveals quieter periods. The thickness of each band hints at warmth and snowfall. The glacier is not a diary with sentences. It is a record in layers. A transmission spectrum behaves similarly. It is a record in bands. Each band forms where the atmosphere becomes thick along a grazing path. Another payoff appears in the way false signals are handled. A single feature can mislead. A consistent pattern across independent regions of the spectrum is harder to imitate. This does not banish ambiguity. It reduces the space of stories that fit. The visual anchor returns to the limb and makes the boundary more concrete. The atmosphere is imagined as nested shells. Each shell has a different clarity. One shell is clear and sharp. Above it, a hazy shell softens edges. The place where light is blocked is not a wall. It is a gradient. That gradient is what the spectrum measures. The core concept of degeneracy remains present without being named. Many mixtures can produce similar valleys. Temperature can deepen bands by expanding the limb. Clouds can flatten bands by cutting off depth. Composition can move the positions of features. The limit of observation arrives with precision and calm. Transmission measures differences in apparent radius. It does not set an absolute reference level by itself. Without knowing where the baseline sits, the thickness of the limb can trade places with abundance. Noise can also imprint shapes that resemble weak bands. Limited wavelength coverage can hide crucial crosschecks. Limited resolution can merge nearby features into one. These limits are not a failure, they are the frame of the method. Another payoff follows from accepting the frame. The strongest conclusions are not single molecule declarations, they are self-consistent atmospheres. A haze that explains a slope should also mute deeper bands. A temperature profile that puffs the limb should also change relative band depths in predictable ways. A heavy atmosphere that contracts the limb should leave a quieter spectrum overall. These are calm constraints that appear from physics alone. The visual anchor becomes a slow sequence of possible spectra. One shows crisp bands with clear spacing. Another shows a smooth curve with only gentle undulations. A third shows deep cores with shallow wings. Each spectrum is a different limb. Each limb is a different layering of gases and particles. The main number appears once with an everyday comparison that stays natural. An extended upper atmosphere can reach about 10,000 kilometers above deeper layers like the span from pole to pole on a mid-size world. This number is an order of magnitude guide. It shows that a seemingly thin rim can have a vast vertical reach. The scale shift widens gently. At the smallest scale, a photon meets a molecule. The photon can be absorbed. The molecule can re-emit. At a larger scale, many such events set the altitude where the slant path becomes opaque. At a planetary scale, that altitude traces a ring around the terminator. Over long times, escape and chemistry reshape which molecules remain to absorb at all. A single spectrum sits across all these scales. Another payoff follows from the scale shift itself. The spectrum does not need to show every detail to be meaningful. It only needs to show which parts of the atmosphere are accessible to light. Some regions are revealed, some are hidden behind clouds, some are hidden by limited precision. Knowing which is part of the reading. The visual anchor softens toward rest. The planet continues its path across the star. The limb ring brightens slightly as the star's edge is approached. It fades as the disk moves away. The ring is always thin. It is always layered. It is always changing with wavelength. The final limit is stated as a gentle boundary of intuition. A spectrum is not a direct encounter with air. It is an indirect shadow cast by physics. Indirect shadows can be interpreted. They can also be misread if treated as literal pictures. The calm method is to keep multiple explanations in view. It is to prefer patterns that agree across bands. It is to hold uncertainty as a normal part of inference. The section closes with a soft landing. The limb remains a quiet arc of filtered starlight. The arc holds molecules, haze, and temperature as a single intertwined signature. The next motion is no longer forward into new mechanisms. It is a slow settling into the steady idea that light passing through layers can carry a world's atmosphere in a few gentle dips.